Hey everyone, Kevin here with some sample problems for exam number 2. Let's go to the first problem. This is a simple conversion, converting 500 calories to joules. So you'll need this table up here, which will be given to you on the exam. And these are simply conversion factors. So here, what we have is calories, 500 calories. All right, that's what we're given. And what we need is an answer in joules. So we need a conversion factor that relates calories to joules, and that's this one that I'm circling right now. We start with calories, right? 500 calories. So we can write that conversion factor. As always, we can write that with either number in the numerator. In this case, we want the joules in the numerator because that is what our final units are going to be, joules. So the conversion factor is 4.184 joules per calorie. And now we just do the math. And so 500 times 4.184 is 2092. And we canceled calories. So our remaining units that we have not canceled are joules. So joules becomes the units in the answer, which is exactly what we want, and we're done. If you have a question about why we're canceling calories here and here, remember that you can always write 500 calories as 500 calories over 1. That's exactly the same thing. So all we're showing by writing 500 calories over 1 is that 500 calories are in the numerator, and that can be canceled with 500 calories in the denominator in the second factor in our problem. So we can cancel calories in the numerator on the left, right here, and calories in the denominator on the right here, where I'm drawing the arrow now. And that's why we can cancel calories versus calories. All right, let's go to the next problem. This problem is a combined gas law problem. So the combined gas law is here, and you will not have to memorize that. That will be given to you on the exam. So you can stop and read this question, but let's just set it up with our initial starting pressure, temperature, and volume. So P1 is our starting pressure, and we have a pressure of 20 psi. Our starting volume, V1, is 2 liters, and our starting temperature, T1, is 25 degrees C, but we have to add to that 273 because with these combined gas law problems, you've got to use degrees Kelvin. So that is 298 degrees K. Our ending conditions, we don't know the ending pressure, right? That's what we want. We're looking for what the pressure is inside the 2-liter container. The volume doesn't change. It's a rigid container. The temperature, however, does change from beginning to end, and that goes up to 50 degrees Celsius, or 323 degrees Kelvin, 50 plus 273. So that's our setup. And so let's go to the next page and we'll lay this all out in an equation. Okay, to set up our equation then, we've got pressure 1, which is 20 psi, times our volume 1, which is 2 liters, and we divide that by our initial temperature, which is 290 8 degrees K. On the other side of the equal sign, we've got our second pressure, which is the unknown. That's what we want to solve for. Multiply that by our volume, 2 liters, and divide it by our new temperature, which will be 323 degrees K. So we have to solve for P2. So we want to isolate P2 on one side of the equal sign. Well, one way to do that is to get rid of the other factors on the right side of the equal sign, which would be the 2 liters and the 323K. Well, how do I get rid of the 2 liters at first? Well, I could divide each side by 2 liters. So let's do that. So 20 psi times 2 liters divided by 298 degrees K times 2 liters, because I'm dividing each side by 2 liters, equals P2 times 2 liters divided by 323 degrees K times 2 liters, because I'm dividing each side by 2 liters, right? So those two factors that I'm adding on each side, I'm circling now. You can always multiply both sides by something or divide both sides by something, and you don't affect the overall result. So that's what I'm doing here. I'm dividing by 2 liters. So let's eliminate now. We've got 2 liters in the denominator here that I'm crossing out now, and we can cancel that against the 2 liters in the numerator here. On the other side, we cancel the 2 liters in the numerator against the 2 liters in the denominator. And now we've simplified our equation nicely. We've got 20 psi divided by 298 degrees K on the left side. And we've got P2 divided by 323 K on the right side. Well, now let's multiply both sides by 323 K. All right, so next is multiply both sides by 323 degrees K. So if we did that, we end up over here with 20 psi divided by 298 degrees K times 323 degrees K equals P2 times 323 degrees K divided by 323 degrees K. So now we see we can cancel 323 degrees K on the right side in the numerator and the denominator. Over on the left side, we can cancel degrees K in the numerator and denominator. So now we just do the math. And what do we have? We've got 20 psi divided by 298 times 323 equals P2. Well, if we do the math, P2 equals 21.7 psi. I'm running out of room here, so I'll squeeze it in here. 21.7 psi. So our ending units that we ended up with here are units of pressure, right? So those end up as the units in our answer. And we wanted to solve for the pressure, so having units of pressure looks good. And we know that the temperature went up, so we know our pressure should go up too, which it did from 20 to 21. So that's how you'd solve one of these combined gas law problems. Next problem, you need to melt a 50-gram block of ice that's now at 0 degrees C. How many calories will it take to melt this to water at 0 degrees C? So this is just a change of state from a solid, from ice to water. And we're not changing the temperature, we're just changing the state. right? So we have ice at 0 degrees C, and we're going to melt that and create water at 0 degrees C. So how do we do that? From lecture, you probably remember that melting, the amount of energy it takes to melt something, is the heat of fusion. So that's shown in this box on the right. You will be given that in the exam. You'll be given those kinds of numbers. So you do not have to memorize those. All right, so we have 50 grams. That's what we know. And we know that to heat up ice and melt it, we have to multiply that by the heat of fusion, which is 80 calories per gram. $80 calories per gram is the conversion factor. And we can write it with the calories in the numerator or in the denominator. But in this case, we want to cancel grams, and we want the ending units to be calories, right? Because what we're looking for is how many calories will it take to melt this. So the way we've set this up looks appropriate. We can cancel grams here on the left and here in the right term. And then it's just 80 times 50. So 80 times 50 is 4,000. Our ending units are calories. The only units we haven't canceled are calories. So that ends up in our answer. And if I've done this right, 50 times 80 is 4,000. And that looks right. That's exactly how you do it. All right, so all we're doing is melting. We're not changing the temperature. We're just melting ice at 0 degrees to water at 0 degrees. On to the next one. This is another energy question. If you have a 50-gram block of ice at minus 20 degrees C, how many calories of heat will it take to heat this to ice at 0 degrees C? So we're not changing state. We've got ice in the beginning. We're going to have ice at the end. All we're doing is heating it up from minus 20 to 0. If you're heating something up without changing its state, you use the specific heat, and that'll be given to you. So in this case, we're using the specific heat of ice, and it's 0.5 calories per gram per degrees C. So what do we have? We start with our knowns, 50 grams of ice. And we know we're going to heat this up from 20 degrees to 0. So we're going to heat it up by 20 degrees Celsius. Our conversion factor here is the specific heat, and it's 0.5 calories per gram per degrees Celsius. All right, for every gram of ice and every degree you increase, you've got to input 0.5 calories of heat energy. All right, have we written our conversion factor? This is our conversion factor here. I'll just abbreviate it CF, conversion factor. Have we written it with the right things in the numerator and the denominator? Well, if we write it this way, we can cancel grams against our 50 grams of ice. We can cancel degrees Celsius in the denominator of the conversion factor against degrees Celsius in that 20 degrees C factor. And our remaining units are calories, and that looks right because we're looking for how many calories of heat it takes to heat this ice. All right, so let me just do the math. It's 50 times 20 would be 1,000 times 0.5 would be 500. So this equals, let's put the equals down here, 500, and our ending units are calories. And we wanted to have an answer in calories, right? That's our one remaining unit that we haven't canceled, so that looks right. And the math looks right, just sort of doing it in my head as I did before. So I think we're in good shape, 500 calories, and that's how you would heat up something when the state doesn't change. In the last problem, the state changed from solid to liquid. In that case, we used the heat of fusion. In this case, the state didn't change, so we use the specific heat for ice or for solid water. If we were taking water and heating it and boiling it, heating it to water vapor, then we would use the heat of vaporization, which is also in this table in the upper left here, upper right. So be sure you're clear on if we're changing from solid to liquid, it's the heat of fusion. If we're changing from liquid to gas, it's the heat of vaporization. If we're heating something up without changing its state, we use the specific heat. So be sure you know that stuff for the exam. See you in the next problem.